All right, yeah, so we're gonna pause those tools right there. And yes, the answer for this one is yes, the positive ion is called a cation. My favorite way to remember this is that if you think of what a cat acts like or what a cat does and how a cat paws at stuff, then you can say that it's pawing or positive like a cation. All right, so cations like to paw at everything because they are positive. All right. So moving on. All right, make sure you get your, I'm sorry, one more thing here. Make sure we are getting our notes out because we will ask you to raise your hand for those notes in a little bit. But moving on just to some disclaimers again. Again, please make sure you do not share any personal information during the live sessions. All right, your participation is vital and required. We want to see you guys learning and understanding what we're teaching you. All right, and just one more thing, just as note that these live sessions are recorded for education.
Sorry, give it a moment. All right, everyone. So taking a look here, we are starting up here our spring break tonight. So you will be coming back, not this upcoming Tuesday, but the Tuesday after that, which I believe is April 6th. All right, so this will be our day back on April 6th. So you get a week and a day off, which is great. Today we're going to be talking about isotopes. I do apologize. Yesterday I gave you a day to kind of catch up on missing and failed work. The reason was just because I was having a hard time uploading the instructional videos yesterday. They weren't uploading with any sound, which is not helpful for an instructional video. So we will go ahead and we'll have an extra work day after spring break to make up for that from yesterday. But hopefully you got to use yesterday and use that time to catch up on anything that was missing. All right, let's go ahead and talk about where we are in our unit.
All right, so our unit today is going to cover something called isotopes. You'll see in a little bit that it's going to be something a little like ions were atoms that had different charges, and isotopes are going to be atoms of kind of like the same identity, but they have different masses. All right, we're about a third of the way through now, so just a couple more lessons and we will be halfway through. And yeah, and as said before, don't worry about Unit 2 project right now. We will find time later on during the unit to catch up on that. All right. So let's look at our agenda today. We will be going into isotopes and ions as a little bit of review and explain how they're different. We're going to learn how to calculate the atomic mass of an isotope, and we're going to explain how the average atomic mass of an element is determined. And then we will go on to identify the most common type of isotope of an element based off of that average atomic mass. And then hopefully by the end, we should all be masters of this subject and we will get good grades on our notes. All right. So move on to some attendance.
So make sure you have your notes open and ready to go. At this point, we sent out the links in the chat. Go ahead and raise your hands. We do need raised hands from 100% of you, or if you're unable to raise your hand for some reason, you need to chat us. So go ahead and raise your hands. I'll give you another 30 seconds to get that done. I see Landon in the chat. All right, let's go ahead and do a practice up here. What I want to know is, what is the main role of protons: bonding, identity, or stability? Protons, do they have a negative, neutral, or positive charge? Where are they located, inside the nucleus or orbiting around the nucleus? And what is its mass, 1 AMU or approximately 0 AMUs, meaning negligible or insignificant mass? Go ahead and circle the correct answers up on the board. You should have 4 correct answers up there. Go, go, go. Get your answers up there. Excellent, getting lots of great answers up there. Perfect. All right, let's go ahead and pause these tools up here. So yeah, it looks like we had a couple mistakes, but we did start to fix them. So taking a look here, the main role of protons, remember, protons are always in charge of identity. Bonding actually comes from which subatomic particle? Tell me in the chat. Ryan, try the other notes. There are 2 links. Try the other link. Tell me in the chat, bonding is actually caused by which subatomic particle? Yeah, the electrons, exactly. So the correct answer here is actually protons are in charge of identity. Remember, we said if you change the number of protons, you change the identity. That's why hydrogen and helium, which only have a 1 proton difference, are still vastly different in terms of their identity and characteristics. That's why hydrogen is flammable and helium is not. They have different identities. Smiley faces emojis in the chat if that correction makes sense. Smiley faces emojis in the chat if that makes sense. All right, there we go. Taking a look here. Now, protons do have a positive charge. We know that the prefix pro right here means like good, right? So pros and cons. Pros are the good ones. And so, yes, this would have a positive charge. Proton is located inside of our nucleus. And because it's in our nucleus, it also has mass, specifically 1 AMU or atomic mass unit of mass, 1 AMU of mass. Anything in our nucleus has mass. Excellent. Let's go ahead and make sure we get this in for number 2. You should have 4 correct answers. Make sure you check off all 4. Otherwise, the computer will mark it as incorrect. You have 35 seconds to get that done. Raise your hands for number 2. Read carefully. Make sure you only check off the correct 4. So we talked about protons. Now we're going to go ahead and review what we've learned so far about neutrons and electrons. So we know that neutrons and electrons both cannot affect identity. We just said protons are the only ones that affect identity. Neutrons and electrons do not. This means we can change the number of neutrons, we can change the number of electrons. It will never change the type of atom. It will still be hydrogen or still be helium or still be oxygen, so on and so forth. Now, they do change some other stuff though. So for example, neutrons, while they can affect mass, because remember, neutrons are in the nucleus and anything in our nucleus has mass. So if you add more neutrons or take away neutrons, you're taking away mass or adding mass to our nucleus, and therefore mass is in fact changing. They have mass. If you change them, it changes mass. Smiley faces, emojis in the chat if that makes sense. Again, if you change the neutrons, you change the mass. Great. Now, on the other hand, they are neutral. So no matter how many neutrons you add, they won't affect the overall charge, right? So if you have a neutral atom and you add a bunch of neutral neutrons, it's still going to be overall neutral. So again, the only thing neutrons are going to change are the mass of that atom. Now, these are what we call isotopes. We said that different versions of the same atom based on its different masses is called an isotope. For example, we have 2 versions of hydrogen right here and in this picture down here. So we have a hydrogen. Both hydrogens have to have 1 proton. Otherwise, they would not be hydrogen. But their neutrons can change. So let's take a look at a hydrogen with 1 proton, always has 1 proton, but in this instance has 0 neutrons. Let's go ahead and calculate that atomic mass. Taking the protons plus neutrons, what is 1 plus 0? Include your units. Units should be AMUs. What is the mass of this hydrogen isotope? 1 plus 0. 1 plus 0 in the chat. Yeah, exactly. We should end up with a mass of 1 AMU. Now, on the other hand, I have another hydrogen. It must be hydrogen because it also has 1 proton. But this time, I'm changing the neutrons. Now it has 1 neutron. So again, adding these 2 together, again, we can ignore electrons. Electrons have negligible mass. So just adding the protons and neutrons, 1 plus 1. Now, what is my atomic mass? 1 plus 1. Don't forget those units. No naked numbers. Excellent. I see Micah in the chat. Ronnie, Monse. Good, Thalia. Excellent, excellent. Yes, 1 plus 1 should give us 2. So we should have 2 AMUs. So again, this one right here would be called hydrogen 1. This one right here would be called hydrogen 2 because they're the same identity, but with different masses. Go ahead and give me a green check, orange X if that's beginning to make sense. Again, this is all review, but I want to make sure we're really confident about this because we will be including it, incorporating it in what we're talking about today. Great. Now, electrons, on the other hand, again, also cannot affect identity because they're not protons. But this time, they can change the charge of something because electrons do have a -1 charge. So if you add electrons, just like adding negative friends to your life, overall, atoms get more negative, just like you yourself would get more negative. If you take away electrons, just like if you take away negative friends from your life, the atom gets more positive, just like you get more positive. So electrons can affect charge. On the other hand, they're on the outside of our nucleus, so they have negligible or almost no mass, so they're not going to affect the mass. Now, as we change the charge, remember that these are what we call ions. So let's take a look at a sodium and an oxygen ion right here. So sodium has 11 protons and 10 electrons. Again, we're ignoring neutrons. Neutrons don't have charge. They're not going to affect our charge. So taking a look here, protons, 11 protons. Should I make that a positive 11? Or a -11. Think about what we just said the charge of a proton is on the previous slide. Should that be a positive 11 or a -11? Thank you, Micah. Thank you, Laura. Get some more answers. Yes, Monse. Yeah, this is going to be a positive 11. And 10 electrons, should that number be positive or negative? This 10, should this be positive or negative? Yes, Micah, Thalia, Ronnie, Dima. Yeah, so this is going to be negative 10. So go ahead and do that math. What is 11 minus 10? What is the overall charge here? There are no units, but you should show me positive or negative. There are no units, but you should show me positive or negative. Thank you, Jalen, Micah, Lauda, Ronnie. Micah, yes, this one is going to have a positive 1 charge. Excellent. Or we could write it as Na. 1 positive. Perfect. All right, now oxygen, on the other hand, oxygen has 8 protons, 10 electrons. Again, these protons will be positive, so positive 8. The electrons are negative, negative 10. So go ahead this time. What would be the charge of this ion? Again, 8 minus 10 is like having $8 and trying to give away 10. You should end up in debt. So think about what that final answer should be like if you're ending up in debt. Yes, you're ending up with a negative 2 charge, or we could say O2 negative, O2 negative. Now remember, from the start of class, a positive sodium ion, a positive ion is called a what? Positive cation is called, or sorry, positive ion is called a what? Gave you the answer. Tell me in the chat. We just went over this. Yes, exactly. This one is going to be a cation, whereas the negative oxygen will be a what? The negative oxygen will be the opposite one. What is the opposite one? The negative ions are called anions. Great. So that's, again, a review from just a couple days ago. All right, let's go ahead and make sure we understand.
All right, so let's practice this a little bit. Let's turn on our whiteboard tools. Let's use our thin lines to match up a term with a definition. All right, it's going to be a little different because now the terms are kind of like an action that we're taking. Either we're changing neutrons or changing electrons. And either one of those two actions is going to result in one of these happening, a change in the atom's charge, a change in the mass, or resulting in what we know as an isotope, or resulting in an ion. So because we have two terms with multiple definitions, we will have multiple lines being drawn from one term. All right, so use your thin lines. Oops, did I just do that on accident? My mistake, everyone. My apologies. All right, now we're back. All right, so let's draw our lines. All right, cool. So looks like we understand this pretty well. So let's check our work. And yes, we were doing pretty well on that. So it turns out, yeah, changing neutrons will result in a change in the atom's mass, or I'm sorry, and it will result in something called an isotope, just like how changing the electrons will only change the atom's charge and will result in an ion. All right, so make sure you mark these answers for number 3 in your notes.
All right, so now we're going to go ahead and talk a little bit about how we actually calculate atomic mass. This is something that we actually already reviewed, but it is related to today's topic, so I do want us to make sure that we are super confident on this. So the question is, what is the atomic mass of an isotope of rubidium with 50 neutrons? Remember, atomic mass is calculated by adding protons and neutrons. We just reviewed that. So it's saying that this isotope of rubidium has 50 neutrons. I do, though, need to know the number of protons, and that is not given to me. I can determine that, though, always from my periodic table. Point for me on the whiteboard. Where do you see the number of protons for rubidium? Where do we see the number of protons for rubidium? Yes, 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 exactly. It's right there at the top. Remember, that's our atomic number. And atomic number is the same thing as the number of protons. So yes, you are absolutely correct. We have 37 protons. So just putting those together, I have 37 protons plus 50 neutrons. What would be my final mass here? Again, I'm ignoring electrons. Electrons don't have enough mass to matter. So tell me in the chat box, using your units of AMUs, what would be the mass of this isotope? Again, there are other rubidiums. You got to add them, Jalen. We're not subtracting, try to add them. Yeah, this is not a charge, this is a mass, so add them. Nope, that's still subtraction, Thalia. Try to add them together. There we go, perfect. All good, fix those, yes. It's all good, that's why we're practicing. Yes, Thalia, perfect, fixing it, I love it. Yes, 37 plus 50 would give me an overall mass of 87 AMUs. So tell me in the chat, what would I call this isotope? Take the name of it and take the mass of it, put it together with a little dash in between. So put the name of it, dash its final mass. Go ahead and tell me in the chat what would be the name of this isotope. Again, there are many different types of rubidiums, but this one in particular is rubidium what? Rubidium what? Go ahead and write it out for me. Excellent. There we go. I see Micah. I see Laura. Ronnie, Monse. Yeah, exactly. So we could say RB37 or even just rubidium 37. So rubidium, and then sorry, 87, not 37, 87, rubidium 87. There we go, perfect. All right, so the answer here for number 4 is just 87 AMUs. So the number should go in the first box, and then the unit should go in the second box. The unit is AMU. Make sure you only write AMU, otherwise the computer will mark it as wrong. So again, first box is 87, second box is AMU. Go ahead and raise your hand when you have that saved. You have 20 seconds to get that done. Thank you, Thali. I see you in the chat. All right, let's go ahead and move on. Okay, so this one we're going to go ahead and actually apply here. So what is the atomic mass of an isotope of silicon with 15 neutrons, right? So we know the number of neutrons. Let's annotate this together, and then you will need to finish it on your own. So based on the atomic number, I do know the number of protons. Go ahead and tell me in the chat, what is the number of protons for silicon? Go ahead and tell me in the chat. Take a look at our periodic table up here. Make sure you are participating. Thank you, Jalen. Thank you, Andrew. Julie, excellent. Yeah, exactly. This one is going to have a number of protons of 14. All right, so taking protons and neutrons, that should help you calculate your atomic mass. Again, the number needs to go into the first box, and then the unit goes into the second box. All right, so make sure you fill that in correctly. Number in the first box, unit, AMUs in the second box, AMU. All right, this is going to be number 5. Go ahead and raise your hands when you have this saved if you want to check your answer. We are in the Q&A area, and I will give you 30 seconds. Go, go, go.
All right, so learning a bit of what average atomic mass is. Atomic mass is on the periodic table already, but it is not a whole number, as we probably have already noticed. This is because this number is called the average of all the isotopes that naturally occur in nature, right? The average atomic mass takes into account what we call the abundance of each isotope that we have here on Earth, right? Often the closest or most common isotope is the one that most resembles the average number that is next to the element. So the type of isotope that is most abundant for carbon is going to be the closest whole number to 12.011, which would be 12. All right, that requires rounding the numbers to whole numbers, and we will get to that in the next couple practices. But for now, just raise your hands for number 6, marking abundance in your notes for that question.
All right, so let's go ahead and take a look at this next question. So this next question, you don't need to memorize this process, but I do want you to be able to actually see the process in action, just so you can kind of understand how this idea of it being closest to the most common isotope is in fact true. So let's take a look at chlorine. Chlorine is made up of 2 main isotopes on Earth. There's chlorine 35, so chlorine with a mass of 35 AMUs, and this makes up about 75% of Earth's natural chlorine. The other 25% is chlorine 37 or 37 AMUs, chlorine with a mass of 37 AMUs. That makes up 25%. Now, in order to actually find the average here, we're not just going to add them together and divide by 2. That's often what we do with averages, but in this case, this is what we call a weighted average, which means you need to actually average it so that the thing that occurs more gets a little bit more of the average, okay? So let's go ahead and take a look at what I'm talking about. So chlorine 35 occurs 75% of the time on Earth. So let's go ahead and put this into decimal form. Now, the word percent literally means per 100. So 75 per 100 or 75 over 100. That is what 75% means. So go ahead, either put that in a calculator, or if you already know this from memory, what is 75% in decimal form? 75 divided by 100. Percent per 100. 75 over 100. Thank you. I see David in the chat. What is 75% in decimal form? Again, it's the same as saying 75 divided by 100. Yes, we should be getting 0.75. All right, now what about 25%? Again, the same as saying 25 per 100 or over 100. Go ahead and tell me in the chat, what would that be in decimal form? Yes, this is 0.25. So now what we're going to go ahead and do is we're going to take each of those masses and we're going to go ahead and multiply them by how often they actually do occur. That way our final average does include the fact that one of them occurs a lot more on average than the other one. So taking a look here, let's go ahead and put in chlorine. Again, chlorine 35, by definition, chlorine 35, the mass of it is 35. So 35 AMUs. And we're going to multiply it by how often it occurs, which is 0.75. Grab your calculators on your phone, on your computer, or Google the word calculator to pull up a calculator. What is 35 times 0.75? 35 times 0.75. See Thalia on top of it in the chat. I see David working hard. Thank you, Julie, Peter. Excellent, Ronnie, Micah. Yes, you should be getting 26.25. Let's go ahead and do chlorine 37. Again, chlorine 37 by definition has a mass of what? Chlorine 37 by definition, the way that we name it, has a mass of how many AMUs? Yeah, of 37. Excellent. So 37. And this time, this one only occurs 25% of the time. So we're going to multiply it by 0.25. And tell me in the chat, what do we get? 37 times 0.25. Yes, you should be getting 9.25. All right, so what I want you to notice here is that we get a lot more from this 35 chlorine because, again, it occurs a lot more on Earth. That's why we end up with 26.25. That's a much bigger number. Smiley faces, emojis in the chat if that's beginning to make sense. Again, the one that occurs more becomes more a part of the average. Okay, so all we need to do is we need to go ahead and total it. So add these two numbers together and that will give us our final average. Add them together and that will give us our final average. So 26.25 plus 9.25, what do I get? Excellent. I see lots of people in the chat coming up with that. Yes, you should be getting 35.5. All right. So again, this 35.5, is that closer to chlorine 35 or closer to chlorine 37? This 35.5, is that average closer to 35 or to 37? Thank you, Andrew. Yeah, it's a lot closer to that 35, which again should make sense because chlorine 35 occurs a lot more. Green checks, orange X's if that's beginning to make sense. Again, that is why these weird numbers do in fact end up closer to the isotope that tends to occur more. Excellent. All right, this is going to be the answer to number 7. As always, in the first box, put the number. In the second box, put the unit, which is AMU. Please raise your hands when you have this saved. You have 25 seconds. Here we go. All that being said, we just said that this funky number at the bottom is closest to the most common isotope. Again, there are many different types of strontium, 84, 86, 87, 88, but one of these is going to take up most of that average. So the way that we figure out which one this is closest to is we just need to round the number to the nearest whole number. So let's review how we round numbers, all right, just in case we need that review. So taking a look here, what we're going to do is we're going to circle the number that we want to round. Now, I want to round to the nearest whole number, so I'm going to take the number that occurs right before the decimal. I'm going to go ahead and circle that. That's a 7 right there, okay? Now, what I'm going to do is I'm then going to look next door to the number after it. So let's take a look at the number after it. If this number is a big number, 5 or more, then our circled number needs to get rounded up. If the next door number is a small number, 4 or less, then the circled number can stay the same. So let's go ahead and take a look here. This number next door, is this a big or a small number? The number 6, is that a big or a small number? Again, big defined as 5 or more, small defined as 4 or less. Yeah, this is a big number, right? So 6 right here is a big number. And so this 7 needs to actually be rounded up. So tell me in the chat, what would be the closest rounded whole number? Don't forget the first digit. It's 80. There we go, 88. All right, so then circle on the board, what should be the most common isotope of strontium? Again, most likely this weighted average is closest to which isotope? Closest to which isotope? Yes, there we go. I see Lauda in the chat. I see people up on the board. Yes, exactly. It's going to be closest to strontium 88. So let me go ahead and, sorry, I'll clear that out. So this would actually end up being closest to strontium 88. Go ahead and raise your hands for this one. You have 20 seconds to raise your hands for number 8. Let's move on. All right, so this one we need to go ahead and finish on our own. I will go ahead and annotate it for you though. So which isotope of sulfur is the most common on Earth? We have 5 options: sulfur 31, 32, 33, 34, 35. Again, sulfur can exist in many forms with many masses. But again, that weighted average is going to be closest to which isotope is probably the most common based on how weighted averages work. So I'm going to go ahead and circle the number I want to round right before the decimal, which is this 2. And taking a look next door, tell me in the chat, is this 0 a big number or a small number? Is this 0 a big number or a small number? Thank you, Thalia. Thank you, Ronnie. Jalen landed. Yeah, this is going to be a small number. And so this number then can just stay the same. You don't need to change it. It can just stay the same in our circled numbers. So that should help you figure out what the most common isotope for number 9 is. Go ahead and raise your hands when you have this saved. You have 30 seconds. If you need help, we're in the Q&A area. Please do not put answers in the main chat.
All right, so good job, everyone. Great job today. We just learned how to define isotopes and ions. We learned how to calculate the atomic mass, find the average mass, and we learned how to name an isotope using that most common mass from that mass that you see on the periodic table. All right, if you haven't already, of course, please submit your notes.